Good morning, beautiful class. How you guys doing? It is 6:30 in the morning and I figured, hey, there's no better time to talk about lattice energy than, well, in class, which we already did, or right now. It's also a good time to throw a ball for corduroy. There you go, buddy. All right, so we're gonna talk about lattice energy. A brief introduction to what it is. Lattice energy is the amount of energy it would take to separate a solid ionic compound into its gaseous ions. And we've talked about ions before and how they like to be in water. This would actually take a lot of energy. But another way to think about it, maybe, is to instead think it would also be equivalent to the same magnitude of pulling together two random gas ions and forming the sodium chloride. So if you have some ions just floating around in space, it's the amount of energy that they would release whenever they're formed into this happy, stable lattice. So if you remember, sodium chloride is not really just NaCl, it's a whole bunch of NaCl stacked together. So when we're talking about a solid, it's actually talking about this three-dimensional structure of sodiums and chlorides stacked together, all happy. And again, it would be a three-dimensional. All right, so cool. When we talk about lattice energy, the things that would affect the amount of energy that it would take to pull these guys apart, there are two things that would specifically affect it. Number one, and there's no particular order to the amount of influence, is size, and number two is charge. Size is also related to the distance between them. And when I say them, I mean the anions and the cations. And all of this is because of Coulomb's law, which essentially states that energy is proportional to the charge of one thing times the charge of the other thing over the distance squared. Now, we're not worried too much about the squared right now. We're just looking at general principles. And the general principle says if the charge between two things goes up, the energy must also go up. If the distance between them goes up, then the energy goes down. In other words, if they're farther apart, the energy to pull them apart is a lot less. It takes a lot less to pull them apart. And that should make sense based on, for example, the demo that we did in class, which just puts two people together. I did a bad job of drawing these people already. Let's see. Let's give this, let's draw a person over here. We can fix this. There's no mistakes, just happy accidents. Thank you, Bob Ross. Okay, so let's say these two have really long arms and they're interlinked. I shouldn't say they have long arms. Their arms are interlinked. They're relatively close to each other and the distance is down. If the distance between them is down, it's going to be really hard to pull them apart. So if you have two people on either side trying to pull these people apart, if their arms are linked and if they're close together, it's going to be very difficult to pull them apart. As opposed to if they have really, really long arms and then their hands are barely touching, their hands are circles. Why? I don't know. Yay! And you try to pull them apart, the distance between them has increased, and it's easy to pull them apart. So difficult. In other words, this would have a high energy to pull them apart. It would take a lot to pull them apart. So pretend this is sodium and this is chloride. And the distance between them increases, it's more difficult. So let's talk about what would cause this situation. So when we look at the periodic table, sorry, my dogs are playing. When we look at the periodic table, the size of the radius of the atoms increases as you go down and to the left. So let's look at two different examples. Hey. Let's look at two different examples. We have sodium chloride versus, let's say, rubidium chloride. So sodium chloride versus rubidium chloride. When you look at the periodic table, sodium is going to be smaller than rubidium. So essentially sodium would be like this and chloride would be like that. And rubidium would be much bigger And chloride would be, again, the same. Chloride should be the same in both situations. Now the distance between them is measured between their centers. So the center of the nucleus. And if you look at both of these situations, this one's going to be smaller and this one's going to be bigger. So if we're comparing sodium chloride and rubidium chloride, and I asked you which one has the most energy or the highest lattice energy, that would be this one. This would be the harder one to pull apart. So this one has the highest energy, and this one would have the lowest magnitude of energy to pull them apart. It's easier to pull things that are apart farther distances. All right, so that was size. Now let's go ahead and talk briefly about charge. So charge is like the attraction between two things. So let's say you have a really generalized example is magnesium oxide. And if you look at magnesium up here, it's got a +2 charge, and then you go over to oxygen, it's 2- charge. Magnesium oxide is really a lattice built with magnesium ions and oxide ions. And so if we take magnesium and oxide and compare it to something decently similar in terms of charge, let's see, or in terms of size, excuse me, like, well, we can even stick with sodium and chloride. Sodium and magnesium are relatively similar in size. Sodium's just slightly bigger. And if you go over and look at sodium, or the chloride and the oxygen, they're both also relatively similar in size. Chloride is a bit bigger, but charge trumps it all. So in this case, we have Na plus and Cl minus. Now to remind you of the relationship, its energy is proportional of Q1, Q2, where these guys are the charges. And over the distance squared. Again, we don't care too much about the squared. So in this case, this one has a larger charge and this one has a smaller charge. Charge, I like to think of it as like the attraction between them. So if you think about this one as having a higher attraction between these themselves than this one, this is twice the attraction. So if this one has twice the attraction, which one's going to be more difficult to pull apart? Well, obviously this one, because they love each other more. This is like this beautiful love story, and this is just like love-hate story, I don't know. So these two totally love each other. They're very highly attracted to each other. As the charge of them goes up, the energy also goes up to remove them from themselves. So this one has the highest energy. And this one over here would have the lowest. Hope that makes sense. Have a good one. Bye.